So, Shannon, I guess it's probably time to start. It's
been
been
5 minutes.
5 minutes now.
Yep. So, welcome everybody to another episode of Humanode Fireside. Today's topic is biometrics and privacy. So, although this is a topic that we've gone over a number of times, it is a very vast and deep topic. So, Dato, shall we start with your opening statement?
Thank you very much, Shannon. Hello, everyone, once again, and thank you for joining us to discuss privacy and biometrics. Actually, I'm not really surprised that this is a recurring theme, because um, many things are happening out there in terms of research, as well as um, we are always striving to provide the principle of privacy on all the data that we're trying to throw around here in the Humanode network. And biometrics are, of course, integral part of it. And as always, it would be interesting to talk about various technological limitations of private biometrics, their origins, history, approaches, and um, today is a very special day because we've been joined by um, members of our encryption team. It's Rafa and Hardik. Hey guys, it's great to see you here, both. And well, they'll be also be able to share some things that they've been working on as well. They're working on something very cutting edge, and if successful, could really change the way we interact with biometrics as a whole. Um, yes, I see Victor is also here. Hey, Victor.
Hey there. Actually, I wanted to start our today's meeting with telling you that after visiting at Dubai, we talked to many people, and usually, for some reason, only venture capitalists say that privacy is something not that important. People don't care about their privacy. Whereas we can see from our community and from the development community that we met there that they respect privacy as one of the main features which is vital for them. And this is at least the third time we are holding the session about privacy of biometrics. And yeah, I'm happy that people value this.
Well, Victor, since you've started from the theme of ethics, right, it will be smart to touch upon the very opinions regarding this, right? So, um, I guess my first question to the people in this chat is, how much do you really care about privacy of your biometrics? I mean, would you be okay if your biometrics, would just would just be open for everyone to see and probably identify you, or is it not? I mean, it will be interesting to hear your opinions about this.
If anybody is willing to answer the question, please raise your hand and state your opinion.
Let me let me rephrase this one. How about we add another variable here? So imagine if the biometrics that you're utilizing basically for something allows you to kind of interact with services and various things around you in a much easier way, and with a very good user experience and accessibility, ease of use, or you would prefer the kind of biometrics that are private, but because of their privacy, they limit um, the interactivity, the easiness of use. So between those two, what would you choose? That's my question.
Oh, I guess for me it is. I guess I tend to side on caution. So even if there's some limitations, personally, I'd rather keep it private.
You
What
mean to
about
say
you?
you mean to say that like privacy is more important than utility?
For me, yes, but I'm not to the point where, how should I say, I'll limit all utility, but um, uh,
So
I would,
the balance is tipped more into the privacy, right, than the
yes,
utility.
yes.
Okay. So what about other guys? What do you think?
Oh, let's just start pointing fingers.
Yeah,
Rafa,
I
what
mean,
about?
Yeah, hello everyone. Yeah, this question has arrived in other meetings like this, other fireside, and I always have answered that for my personal use cases, I don't use my biometrics at all in any device or anything else. Just for let's say the government who takes your fingerprints for voting or anything. That's the only case where I have been taking my some biometric data from me. But for in any case, I always value more privacy than usability.
and what about you, Victor? Do you value privacy more than usability as well?
Oh no, I want to experiment with stuff, even if I have to put my privacy at stake only if there is good liveness detection.
Well, as you can see, the opinions are really differ. I guess they are really keen on what profession the person is utilizing and what services he's interacting with in his daily lives. But I mean, um, even our partners from FaceTag always say that privacy is a secondary issue for them, and well, that um, most of the users interacting with centralized biometric services or just pretty much don't care about privacy at all. And I'm wondering how many people are out there who would be willing to interact with biometric systems if they were properly private and properly decentralized. Like how much it would enlarge the interaction of people with um, biometrics as a whole. Maybe there's like a, 50, 60% of people out there who are just not interacting it because of reasons stated by Shannon and by Rafa here. And it really shows like non-inclusion of uh, the people who care about their privacy into the biometric market, and thus their limitations on interaction with various machines through easy authorization schemes using biometrics. Now, talking about private biometrics, like is it's like talking about an encrypted biometric form. They're also called like privacy preserving biometric authentication methods. And I guess Rafa or Hardik can talk about this better than I do. So, Rafa, it would be, it would be interesting to hear your explanation about the crypto biometric approach. Like, how would you define it for the broader people here?
Yes, of course. Actually, in Humanode, we have split the task into two cryptography main uh, research lines. That will be the encryption itself and the verification of the calculation. Because uh, in our case, in any case, you need to assure that the people it's doing the calculations correctly, but also it is protecting what it's meant to be protected. So in a formal environment where you have a central authority, uh, this authority generates some keys, and the user can in somehow encrypt his own data and send it, and this authority will verify that everything is correct. But when you have a group of nodes, in that case, the situation it changed because uh, you don't have one central authority. You have a different methods for doing this. And in Humanode, we call it is collective authority. So in the cryptographic side, what is happening is that we are taking the biometric feature vectors that is generated by a neural network, and from there we are encrypting it using what we call homomorphic encryption. This is a kind of encryption that allows you to perform calculations over the encrypted data. And this is very interesting because you are doing calculations without decrypting the data itself. And how this is possible, because there are some mathematical primitives that allows us to do it. And there is a formal proof that we can uh, assure that these calculations are correct. And the idea is that um, you take your image, the neural network extract from there the feature vector, and this feature vector is associated uniquely with your face. So anyone who can uh, intercept this feature vector can, in a way, not exactly reconstruct your face, but uh, it will be possible to authenticate as it will be yourself. So this is what we want to protect in order to preserve the privacy. So it everything reduced to protect the feature vector. Then this feature vector, we want to send it in encrypted form with a robust encryption scheme that anyone can uh, vulnerate. And we want that this collective authority be able to uh, compare it with another encrypted feature vector. So if there is a matching, you are authenticated and can enter the system. And basically, that's the high level idea of what we are doing. Also, we want to assure that the user are doing the calculations correctly, that there is nothing, because you can say, well, the user can generate something that looks like an encrypted feature vector and send it, but this may be hard. They can tell us how we are preventing that this can be done.
Yes, sure. Rafa, thank you for your high level explanation. Although I think for some people out there, this is not high level. So, before we move on to asking Hardik about how we prevent the data loss, it would be kind of interesting to talk about the primitives that you have to, uh, well, you basically have to work with uh, in your research. Like, do you take into consideration like things like accuracy, speed, or privacy as a what other primitives there might affect what you're basically doing.
Yes, of course. There are several homomorphic encryption schemes, and we are using uh, uh, that is called that is based in a problem called ring learning with errors. This is a problem, a hard problem in mathematics that assure that no one can get the keys or the ciphertext.
Mm-hmm.
There are several, like we say, flavors from this scheme, and the one we are using is warranted that it is fast enough to be performant in a device, but also have the security level required in this case. So we are using 128 bits of security. That's an standard measure for the security in cryptography, and that
And
assures that
what do those beats represent?
that represent the if anyone the probability of success of an attack will be 1/128.
Yeah.
uh, that's a really small number, so the probability of success of an attack in this case is really small. So you know that perfect security it's not doesn't exist, but we always
Mm-hmm.
want to take it to the minimum possibility, and that's what the security parameters tell us.
Okay.
Uh,
Before we move on, I would like to define for our listeners here the difference between plain text and ciphertext once more. So, basically, as Rafa has already mentioned, when a person goes through, any biometric authentication, there's like a biometric feature vector or a biometric template extracted from the computer vision data, and basically it turns into code or some line or hash uh, based on the modification sequence. And when it is explicitly shown and you can see it, it's called plain text. And Rafa was referring to ciphertext. It's basically this biometric template, but gone through some encryption scheme so that it remains its initial variant. It remains encrypted, and the two forms are called plain text and ciphertext. Yes, Rafa, thank you. Please continue.
yes, and the form of the ciphertext, for continue your explanation, it's basically a polynomial. So we are working with polynomials with coefficient in a very special space in mathematics that it's called a finite field. So the hardness of the problem reduced to solve polynomials, basically. So solving some equations in terms of polynomials with coefficient in a specific space, it's hard enough to modern computer to assure us the security. So basically, the security reduced to the hardness of a mathematical problem, and that's how basically every cryptographic schemes works actually. Because you know, maybe you have heard of RSA or elliptic curves. RSA is based on the hardness of factorization of prime numbers, big prime numbers.
Hmm.
Yeah.
Okay. So, for more context, right? Um, Basically, it is usually presumed that any encrypted schemes, compared to plain text schemes, lack privacy, right? Or not privacy, but precision. So let's remember some basics of biometric search and matching operations. So there's like one-to-one matching, where basically you have to match an individual person's biometric template against like one single data store in a database, and basically you know where it is and you find it immediately by some tag and match it to one place. It's called one-to-one verification. And there's also one to N. It's like identifying an individual in a data store. Like you have to go through the database, and you have to match this biometric template against many and find it in a database. So uh, what Rafa was referring to as polynomial is basically the way you go to search through the database. Rafa, can you explain what types are there when you're basically going through like linear, polynomial, and stuff like this?
Yeah, no, the polynomial is what we call the form of the encrypted message. But the encrypted
Yeah.
message can be in any form. Usually, it's reduced to some kind of numbers, X number or binary numbers. But in any case, we treat it like polynomials because every each coefficient means something to us, and then we have a huge polynomial that represent the encrypted form of the feature vector. And again, this connection with the neural network is very interesting because the neural network give us this template or feature vector, and in a traditional authentication system, bio-authentication system, a banking, or like I say, the government for the fingerprint or anything, uh, this is only secured by the communication standards TLS, SSL. But when this authority store it in a database, they store it in plain text. So the
Yep.
security reduces on how they secure their database, but the actual feature vector or anything, it's not encrypted. In our case, we will have this database of encrypted feature vector in every node of the collective authority, and we don't know which node is malicious. So in every case, we'll need this to be always encrypted. And yes, this is just a bunch of numbers, but when we take it, we can perform calculations with it because this calculation, this polynomial calculation, specifically addition and multiplication, are the ones that allow us to match the vectors. When they authenticate, if there is already an encrypted feature vector stored in the database, then this process it's run again. And for the matching, we perform several calculations. And actually, for the ones who remember algebra and their mathematics in high school, they maybe can remember what inner product is. And we take the inner product, and from there we know that there is some element that allows to make the matching with high probability.
Yeah. Um, Rafa, thank you very much for kind of explicitly explaining our approach on a higher level. And Hardik, would be interesting to hear your take about the crypto primitive and math equations that you're utilizing in our soon to be built software-based uh, crypto biometric scheme.
Yeah, thank you, Dato. Yeah, so at the start, you asked this question, right? The given a choice whether one should choose utility or privacy, right? But I think there can be a third choice as well. That will be utility with privacy. So in terms of our biometric authentication, if we see the utility will be providing or performing authentication process using biometric, and privacy means keeping the biometric private, right? So what we are building is providing utility while keeping the privacy intact. That is keeping the biometric data private and still performing the authentication process. So here, I think Rafa has explained most of the part in matching algorithm, where we take the feature vector and encrypt it using some encryption scheme, and then we perform matching process over the encrypted data. But before encrypting the feature vector, there will be a process called feature extraction process, where user will provide its face image or some video frames, and from that neural network model will fetch out the feature vectors, and then that feature vector will be sent in encrypted form. Now this whole process of feature extraction will happen on the user side, and in certain scenario where if user is malicious or not trusted, then one cannot trust this feature extraction process as well. So here as well, we are making sure that no matter whether a user is malicious or not, but the process has to be done correctly. And if the process of feature extraction is not done correctly, then receiver can uh, find that out by verifying certain parameters. So here we are actually building zero knowledge proof system for whole neural network model to ensure that any node, whoever is performing feature extraction of biometric, is doing it correctly and not adding some malicious parameter.
Yes, so basically, um, it's utilizing homomorphic approach on
Yeah,
the.
so yeah, correct. So if you look at most of the zero knowledge proof system, they are relying on some kind of homomorphic properties, not explicitly on homomorphic, maybe not on homomorphic encryption, but eventually it boils down to either additive or multiplicative homomorphic properties. So I think many of us now knows about this ZK sync or ZK stack or ZK snark, and most of them are used to validate or verify the transaction on blockchains. So this itself a complex proof system, and still only used for verifying the transaction, which I believe is not as complex as neural network. But when we go at the neural network level, there are lots of complexity, like different layers, and then different vector computation or floating points like that. And there we need to build up the zero knowledge proof system.
And guys, it will be interesting to hear about the problems and limitations of trying to match biometric templates through ZKP. Like, what problems were you been running into?
Yeah, so first problem I remember is that g- uh, if you pick any zero knowledge proof system or encryption method or anything, all of I think most of them or all of them works with integers only and not the floating point. But if you go to the biometric template or feature vector, and it is always going to be floating points, and that's why we first need to convert that floating point neural network into some kind of quantized neural network so that it outputs a feature vector with integer form, and then we utilize this integer feature vector to encrypt it
So you mean to
and
say there
perform
are
matching.
two transformations of type
Yes. So
in the
we
process?
instead of transforming the feature vector
Oh,
floating point feature vector to
oh,
integer,
oh.
we we are directly transforming the neural network itself. So we are making it quantized neural network.
But I
So
mean,
neural network will, yes. Go ahead.
so the neural network gives is there not like cannot like gives out the floating point, or there could be a layer where it converts the floating point into integer specifically.
No, so the neural network will at each layer it will transform the floating point to integer, and then eventually
Mm-hmm.
we will
Okay.
finally get the integer. Yeah.
Uh-huh. All right. What other limitations and problems you can, you know, describe?
Uh, yeah. So another limitation is so probably will be the accuracy part, and with the
Mm-hmm.
quantized. So this is like straightforward that if you approximate floating point with the integer, then there must be some loss in the accuracy, and we expected some loss, but when we actually perform with the quantized model, the loss was not that significant enough. But now we need to test it out with actually after applying the zero knowledge proof system. So this accuracy test was done without applying the zero knowledge proof system, but we need to still test it out after applying the zero knowledge proof system.
Mm-hmm.
Uh,
Yeah. That's also very I would say that the accuracy drop is the most scourging problem of development of crypto biometric approach. And I mean, there has been a lot of different ways of how to achieve proper precision. And I mean, Heidi, can you explain what else besides from the conversion of the variable types affects precision?
uh, yeah, so not only the integer transformation affect the precision, but probably uh, at some point we are performing encryption and then performing the inner product calculation and then going to matching process, right? So in this part also I expect to lose some bit of accuracy, mainly because when we go from inner product to matching part in plain form, and when we go from matching inner product to matching part in encryption form, there it will be slightly different because there will be a division perform computation, and when you compute division computation over encrypted data, you expect some bit of loss in the accuracy part. So this also needs to be tested out, but I'm hopeful that the accuracy loss will not be significant. I'm not so maybe Rafa knows some additional part. As far as I remember, these were the few things.
Yeah, maybe also the efficiency, because there are some heavy calculations, and in some point when we generate the keys, we also uh, define the parameters. There are several calculations that are only done performed once in several times, or not every time that the user are authenticated, but there are calculations that needs to be performed in the collective authority that are maybe take more than the expected time. But in any case, the performance for the user also may experiment slight difference with the current approach with face tech, because we are taking not only the encryption but also the zero knowledge range proof, and these are sometimes calculation that not only for the case of not only for the conversion to the quantization, but for the specific cryptography calculation itself may take some time, and we hope to minimize this while preventing this. There is a trade-off between accuracy and also between the time or the performance of the scheme. So that's something that we need to take care and carefully manipulate the parameters in order to not lose any security properties, but also keeping it usable in some case.
And to kind of understand the context here, right? We're actually discussing one of the newest approaches to, private biometrics, and to be precise, we're talking about using the machine learning models to, like, with homomorphic encryption to generate, future vectors, and then encrypt them. And this is like homomorphically encrypted approach, but it will be also interesting to touch upon the various approaches that were used prior to homomorphic one. And um, Rafa Hardik, if you allow me to kind of guide our listeners here through approaches that were before, it would be cool. So, yes,
Yes, go
sure.
ahead.
So, well, unsecure biometric data is, we talk about, it's very sensitive to their nature and how they can be used. And uh, before, our third millennia, like in the like um, in the latest decades of the 20th century, right? Um, Implicit authentication was like a very um, it wasn't common practice as it is now. Basically, when you're using passwords, like your user may prove knowledge of password without actually revealing it, right? And your passwords match, it means that this person is the one who created the password, and then you can authenticate it. Now, what was the difference about biometric measurements? You see, biometric measurements of the same person may really differ. And this fuzziness created by biometric measurements renders this implicit authentication approach useless in the biometric domain. Um, Similarly, private equality testing, where there are several devices, or like two devices or entities that want to check whether the values that they hold are the same without presenting them to each other or to any other device or entity. This is like, well practiced, and this solution has been published many times. However, since two biometrics of the same person may not be equal, these protocols are also ineffective in the biometric domain. For instance, if the two values differ by some bits, for example, like n bits, then one of the parties may need to present two ends of the candidate values to check. And uh, since 1998 to 2018, there were four major approaches to private biometrics besides homomorphic encryption and using convolutional neural network to um, encrypt something. And those were feature transformation approach, biometric crypto system approach, um, biohashing, and two-way partially homomorphic encryption. Um, I don't know, Rafa, Hardik, would you be able to add more?
I think that covers most of them. Probably, I'm not sure whether CryptoNet part will be one of them or not. So, CryptoNet is you build a neural network in such a way that the neural
Mm-hmm.
network itself takes encrypted image, and then it's output the feature vector in some from encrypted form. So earlier, when we started working on this, so we thought of the model where user will encrypt its face image, and it will send it this encrypted face image to some other node. That other node will perform the neural network part over this encrypted image. And so there are theoretical work for this, and this can be done using some uh, uh, using CryptoNet, which uses homomorphic encryption. But this whole process drops the accuracy a lot, and in biometric system, we cannot afford loss in the accuracy. So we dropped
Mm-hmm.
that idea. Yeah.
Yeah, that's one of the approaches, right? Um, one of the first, so to say, crypto biometric steps was actually made by IBM, and I guess it was like the first use of indirect biometrics. It was actually uh, proposed by Davida et al. In 1998, but it was like just about future transformation. And then IBM's special computer vision division came out with cancelable biometrics. So it's like um, you basically um, provide biometrics that are easily canceled if you're compromised. That was their main notion. So um, your biometric templates were unique for every application, and that if lost or compromised could be easily canceled and replaced. And they made the solution through providing higher privacy levels, uh, but by allowing several templates to be associated with the same biometric data. Uh, and you allow like various biometrics to the same various templates to the same biometric data, but you store only one transformed hashed version of the biometric template to one application. And at the time, they were considered very useful because of their diversity, of their reusability, and of the one-way encryption that was utilized at the time. Mm, but specifically, like two cancelable templates uh, couldn't be used in two different applications, and you could straightforwardly revoke or reissue your template if you're basically compromised, as I already mentioned. Um, what do you think are the limitations of this approach, Hardik, Rafa, about having one-way transformation for different applications? Okay.
Yeah, can I hear the guys as well?
Okay. Yeah. Uh, yeah. So the one-way transformation is you can say equivalent to hash function or hashing your biometric, right? And I'm not sure how much accuracy this will preserve or not. So because when you look at the hashing biometric or any other kind of transformation, this will always going to affect the accuracy. And other point I see is that probably this will also require either trusted setup or some trusted authority to perform or keep the one-way transformation secret or something like that. And in our scenario, there is no nothing called trusted part.
Continuing talking about the feature transformation approach, the cancelable biometrics actually evolved into a thing called biohashing. Um, it was published by some very good Chinese um, biometric encryptionists in 2004. And basically, what it did, it combined like biometric features with pseudo random number, like Tyrian. And basically, the biohash combined the biometric template with the user specific pseudo random number, like the Tyrian. And it produced a set of non-invertible, like binary bit strings that were thought to be irreproducible if both the biometric template and this number random were not presented simultaneously. Uh, and well, at the time, this approach was like had a lot of traction. It was hyped because this technique had achieved equal error rates. It's like had the same error rates as if it was plain text, and it's called perfect accuracy in this regard. Um, well, however, only 2 years passed, and some professors from Hong Kong University um, that the biohashing performance was based solely on this randomly generated number, and introduction of any form of biometric template in this regard was meaningless, since the system could be only used with this generated tokens. Yes. So this is subdivision of the feature transformation approach from cancelable biometrics to biohashing. Then it would be interesting to touch upon the biometric crypto systems approach, which already was kind of described by Rafa about uh, basically developing a crypto system with secure cryptographic keys using biometric features, right? And um, you basically directly generate cryptographic keys from biometric features, and um, biometric crypto systems used cryptography to provide the system with these keys and the protection of them, and used biometrics to provide with the system with um, dynamically generated keys, which in reverse secure the template and the biometric system itself. Um, and Rafa, it would be interesting to touch upon how uh, this approach evolved, and also um, what are its limitations.
The limitations of our current scheme.
Yep.
Yeah, well, we are developing this specifically for the feature vectors. The limitations are basically, we have talked about the accuracy of the model in general, and also
Yeah.
the performance. But also another limitation is related with the processing time of the for generating the keys and for generating
Yes.
the encrypted vector, and also for authentication itself. So maybe we will face some no problems, but yes, but something to take care of when we implement this in our system, in order that the user doesn't need to wait too long for uh, uh, the running the authentication, because we already know that the inner product calculation that involves some polynomial multiplications are heavy. It will take time, and also this process is interactive and needs several nodes to be online for this to happen. Not every node, but just a specific amount of nodes to be online. And this is also could be a limitation, because we are also have been discussing this issue if the nodes that will participate as a collective authority, what if some number of nodes will drop in the communication or anything happens, and then what about this process for the user? So this is also a limitation. We will need a number of nodes to be online to process this, and what time it will take is also something to think about.
So yeah, thank you, Raf. Basically, you've stated again, it's accuracy, precision, and processing speed, right? So the three of them where are their limitations of the crypto systems meet. And my question is, Rafa, what are the variables that affect the processing speed the most if we compare it to the plain text system?
That affects the processing time, did you say?
Yeah, the processing time. Yes.
Yes. Well, as I say, the calculations for uh, in the crypto space, in the encrypted space, and that calculations that are in polynomials, and they depend on the size of the encrypted form of the feature vector. All the feature vector will be about the same size, but the polynomials for the encrypted form will be bigger, and the size of the variables and also the kind of the calculations will affect the processing time.
Yes. So, guys, let's once again remember the steps taken in terms of the evolution of approach in encryption and biometrics. So, first we got like future transformation methods, which include countable biometrics, then evolving into biohashing. Then we have the growth of crypto systems, where various encryption and decryption schemes were used, but the biometric template shifted from the ciphertext to plain text. Then some fully homomorphic or partially homomorphic sequences were introduced, were introduced, and well, the latest viewpoint is utilizing neural networks to with different layers to actually encrypt the biometric template. And basically, guys, today we're talking about the last step and in the evolution of these approaches. And yes, uh, thank you very much for listening to this difficult theme for this fireside. I think it's already almost time that we wrap up. So, if you guys have any questions to Rafa, Hardigon, or any other of us, please, you're welcome to ask them.
Yep, feel free to raise your hand, speak up, or type it out of the chat.
I guess everyone is shy here, Shen. So,
Well,
or tired.
or yes, mental fatigue, trying to figure out
What the hell was happening here
how
right
this.
now?
Yes.
But okay, I guess the most interesting part is which we don't like forced the guys here to you know declare. But um, when do you guys think and what have has to happen or move so that we have proper software based encryption schemes for biometrics? Like, what are the major challenges for you right now so that this scheme becomes a reality?
Well, my guess is for both Rafa and Hardik is a steady supply of strong coffee and some chocolate to go along with it. That and enough time and they'll do it.
Yeah, that's for sure.
Oh, Rafa, um, looking forward, um, what do you think will allow you to allow you and Hardik to basically make this a reality? Is it just time? Do you need more people? A happy environment to work in, or just more coffee?
Yeah, time, of course. More people to bring this to reality, and always the coffee, always.
What about you, Hardik?
Yeah, so I believe we are on the track, right track, and one part is almost done, and we will soon moving on to the next part, which will be uh, zero knowledge proof for neural network. Yeah.
Okay, well, thank you very much, and thank you everybody for joining us here in this episode of our Fireside. Dato, do you have any last comments?
I'm just saying that the way we interact with various systems right now in terms of biometrics is completely not private and cannot be private because um, of either legal implications or technological limitations that we have. As Rafa mentioned today, one of the only approaches that existed before this is assigning the key to a centralized authority. Well, um, basically research into how do we take this key from a centralized authority and um, give out to many nodes in the system is what guys are trying to figure out, and it's almost like well, it's not just almost, but it's like a research that has not been done thoroughly, properly, and there are no real like methods that you can just use and take. And our guys here are, well, creating new signs as they go. So we all should support them and uh, in their endeavor to kind of create this biometric scheme, because it's really hard.
Yeah, and it's not only really hard, but this is one of those things that I believe sometime in the hopefully near future that will be recognized as one of the most advanced schemes that will propel new, not only new businesses, but a new use for biometric authority. So I'm really, really happy to work with the team and and proud to be a member of it. Victor, do you have any closing remarks?
Oh yes. People sometimes don't understand, but I mean, it has always been either KYC or just a paper wallet, and something that is happening here, which wasn't technologically possible before, is self-sovereign identity without KYC feature, but which has pretty good structural identity solution for the internet. Yep, that's pretty much it. What is going on here without encryption details?
Okay, well, thank you all. Thank you, Rafa. Thank you, Hardik, for joining us. It is always wonderful to have you here. And once again, thank you for everybody who is listening to this. And we'll see you again in 2 weeks. Thank you.
Bye.
Bye bye. See ya.